Last time I used a fact, and so what we will do today is graph sparsification in dynamic stream. Right? So this is a fact which I used last time. This is due to Karger, is that if G has at most, so what is the fact? Any graph G has at most n to the power, like there's some constant Cn to the power 2t by lambda cuts of size t, where lambda is a min cut, where lambda is the size of a min cut. Okay. So if you recall the algorithm for the min cut due to Karger, what did Karger's algorithm did? At every point of time, we contracted, so we uniformly at random picked an edge, contracted it till we had two vertices, and we said if C is a min cut, then probability that C survives is at least 1 over n choose 2, right? So algorithm was very simple. Every time we picked an edge uniformly at random, contracted it till we got two vertices, and then we deleted then we outputted the edges going across these two vertices as our min cut, and then we analyze that if C is some fixed min cut, probability that C survives this process is 1 over n choose 2, and this implied that the number of min cuts is at most 1 over n choose 2. Okay? Okay. Do you have any question? Then ask. Do you have blue pen here?
Sir, there is no blue, sir. There also there is no blue. I went and asked them. I've asked Johnson to buy. Red and green is only there.
Okay, fine. Then I'll get it from my office. I have. लॉकिन वो ब्लू था क्या? वो जो पेन क्या था, ब्लू था या रेड था? Okay. So now we would like to prove something of this. Okay. So rather than doing this, let's try to say that let's try to prove the following thing: is that we are going to call an alpha cut. So a cut C is called an alpha cut. Okay. If the number of edges in the cut, number of edges in the cut is at most alpha times lambda. So like it is alpha times the min cut, okay, alpha times the min cut, okay. Then I'm going to call this as an alpha cut because it is just alpha times more than the min cut, okay. And what we'll try to show that the number of such min cuts are bounded by some good number, and then putting it here accordingly will imply this, right? Okay. So now I'm just going to modify the Kargar's algorithm. I'm going to run the Kargar's algorithm till run Kargar's algorithm till we have 2 alpha connected components or 2 alpha vertices. I mean, y connected component, 2 alpha vertices. Okay, until Kargar's algorithm till we have 2 alpha vertices left. Okay, 2 alpha vertices left. Okay, now given an alpha cut, okay, so this is my algorithm at the end, right? And so I at this point of time I don't know, okay, okay. So now, so we are running Kargar's algorithm till we have 2 alpha vertices left, right? Now what we will do at this point of time is that uniformly at random, choose a partition, right? Uniformly at random choose a partition and return edges between them as min cut, as alpha cut. Okay. So what I'm going to do, I have an edge, I do the same process, uniformly random I pick an edge, contract, until unless I have some 2 alpha vertices left, okay, 2 alpha vertices left, okay. And then what I do, I randomly choose a partition of this uniformly random partition, means one guy in the other guy, other in the other side, and I give you edges which are going across this partition. Okay, so this is what the algorithm does, right? So first notice that if I can show that with very good probability, so you fix some C, okay? If I can show that C survives as across edges, like C is never contracted with very good probability, then with probability 1 over 2 to the power 2 alpha, I am going to output that cut, right? Because I am going, there are only 2 to the power 2 alpha partition, and I know at least one of this partition is good. So at least with this probability, if C has survived, okay, look at C, if edges of C has survived, then definitely with probability at least 1 over 4 to the power alpha, we will output C, right? Okay. So all that we need to show, what is the probability that C survives this process, okay? So for I between less than equal to 1 and n minus 2 alpha, right? So like I'm going to do this process. Let Bi be the event that the edge contracted in ith step in round I is outside C. Okay, so I'm not going to, okay, or rather let's say contracted right round I is from C. I is from C. Okay, so what is the probability of happening of Bi? Right? let's say alpha times upper bounded by alpha times lambda, right? Because I'm going to pick an edge from my C, that is upper bounded by alpha C, times how much? Wait, n minus I minus 1. So this is basically, you should think of this as n into I minus 1 by lambda divided by 2, right? Because min cut is at least lambda, right? So minimum degree is at least lambda, so number of edges in my graph is at least as much. It could be much more, but it cannot be less than this. If minimum cut is lambda in my graph, right, then the number of edges that is left is this much. Because look at any vertex, right? I mean, if I delete all the edges incident to that, that also gives you to cut, right? Okay? Which is equal to, right, alpha times lambda into what is this? It should be equal to, let's see, it is this, okay? So which is equal to 2 times alpha times n minus I plus 1, okay? Because look, every vertex has degree at least lambda, so number of edges in my graph will be at least this much, right? So if I divide by bigger quantity, I mean, I only get smaller number compared to this, okay? So this is it. So what is the probability that, suppose whatever I have output is S, right? So suppose, and return an edge between them as alpha cut, say S. So what is the probability that S which I have returned is C is nothing but at least 1 over 2 to the power 2 alpha of finding this, and then product over I going from 1 to n minus 2 alpha to the power n minus I plus 1. This is exactly, sorry, 1 minus this, right? Because this is a probability of success and this is a probability of failure that which I have bounded, right? So probability that I am going to get C is same as probability that I am not going to get BI as my event. So it is 1 minus this, which is equal to 1 over 4 to the power alpha product going from I equal to 1 to n minus 2 alpha. This is like n minus I plus 1 minus 2 alpha divided by n minus I plus 1, okay? So if you do this, this is like a product which is like that will get cancels after some point of time, and what will be left is 1 over 4 to the power alpha. I am not going to do this computation for you, is like n minus 2 alpha factorial, right? This is what will be left, right? And into 2 alpha factorial divided by n factorial. This is exactly what will be left. Because put I equal to 1 here, right? What is this? I equal to 1, so n, right? Next will be n minus 1 till when? Till certain point it will survive, and then after that things will start getting cancelled, and from there something will be left, something. So you will get exactly this, which is nothing but equal to 1 over 4 to the power alpha 1 over n to the n choose 2 alpha, okay, which is greater than equal to 1 over 4 to the power alpha n to the power 2 alpha. What? Yeah, lower bound or upper bound? This number is at least this much because this is a bigger quantity than this. Okay. Okay. Look, this is not what I wanted to prove. I mean, this is just I gave you a proof, but this is not something which I mean, this is something which you should just know. Now notice that my constant will be like this. So this implies that the number of alpha cut is bounded by this number. Okay, this implies that number of alpha cuts is at most 4 to the power alpha n to the power 2 alpha. Okay, now if I am looking for a cut of size t, right? So t is like 2 alpha. No, t is like what? Alpha times t is like alpha times mu for us, right? T is like alpha times mu, right? Because I'm looking for this. So now, so what is alpha? T over mu. This is what it is, right? T over. Did I do something? No, no. What I'm writing here? Alpha times lambda. So T over lambda, right? So alpha is T over lambda, right? So this is what you get n, right? 2 times T over lambda, right? And a constant is your, this 4 power alpha is your constancy. Okay. So this is how you prove this lemma. Okay. So it's basically Kargar, you run it for certain amount of time and then you just take two partition. If you remember when we were doing kb cut, right, we were stopping till 2k size, 2k, like this is how you prove that upper bound on number of kb cuts, or you get an algorithm. You stop till when the number of components are like 2k, and then we were taking all kb partition of that, right. This is how we got k power k times n to the power 2k. But here we are only looking for a cut, so you only do 2 partition. Right? If you're looking for 3-bay cut, I would have done 3-bay part here at this point of time. Okay, so that's it. So this is how you prove that the number of cuts are small. Okay, so this fact we used last time in the proof of the following lemma. Okay, so which I will tell now, and then we will see what happens. So what did we say last time? We actually said that look, if you look at a graph G, so basically the lemma which we proved last time is a look at a graph G, okay? If lambda is more than some ordered log n, okay? So if the min cut is too large, and then you get a graph G prime by sampling each edge with probability half, then what property did we have about G prime? The property which we had about G prime actually was that look at any lambda A times G. It means, what does it mean? Look at A and look at the edges which are incident, and G was unweighted graph. It is important that we started with unweighted graph. Okay. So the lemma which we proved that if this is too large, min cut is too large, and by too large we meant order log n, then what I can do starting from G, I get to a G prime where I have sampled each edge with probability half. Okay, then the property which we had is that, oh, then look at the lambda A of G, lambda A of G prime, then it is same as in lambda G, 1 minus epsilon, and it is same as this, but it is 1 plus epsilon by 2. Right? Because in expectation half the edges are in the cut, and what we proved using Chernow bound and using this bound, that the number of such for any A subset of G, this is not too much. Okay, and now you might see that for a Sparsifier what we need is greater than equal to this. You can just divide by 1 minus epsilon and do this. So we will just not worry about it. I could just divide by 1 minus epsilon here and get another 1 plus epsilon prime and not care about it. So we will live in this regime. Okay, so this is not a big deal converting this. Okay, so precisely what we proved. So this is exactly what we proved, right? I mean, we had some constant epsilon, blah blah blah, but the algorithm was pretty simple. That if my graph has big min cut, and by big min cut is logarithmic, then if we sample each edge with probability half, then what we get actually samples like, then if you look at the cut here and cut here, they are just by factor 2 away. If they're factor 2 away, then it gives us a very natural way of giving weights to edges of G prime, which is like give every weight 2, right? So that should approximate this cut precisely. Okay, so let me write it down just for your lemma, and let's see what static sparsification algorithm we will make, and then we will try to make it dynamic. Okay, but this is what is important to remember. If the min cut size is large, then we can apply Chernoff to show that randomly sampled subgraph of H has all the good properties of a sparsifier. Okay. So precisely what we prove is the following lemma. Let G be an unweighted graph. Okay, let G be an unweighted graph with min cut size lambda, which is greater than or equal to some quantity lambda star, which we set last time is 24 epsilon square ln 2n ln 2n square c something. Okay, this is what we set. Okay, so this is like something which comes out of the proof, but so don't worry. This is for us, it's like order. So the best way to think of this is order log n by epsilon square. This is it. Okay. Okay. So what does it mean? It means basically that, look, if you want to really go very, very close, then I need to like hope you need to have lot many more edges if you really want to go very, very close to the what do you call the cut size with respect to everyone. Okay. With min cut, at least min cut lambda, which is greater than this number. Okay. Then construct G prime, okay, by sampling each edge with probability half, with just probability half, then lambda A of G prime, and by lambda A, what did we say? It is number of edge between A and B minus A, okay? This means number of edges, not weighted, number of edges between A and V minus A. So lambda of A G prime is less than or equal to 1 plus minus epsilon lambda of G divided by 2, okay, for all A subset of Vg, right? So this statement is true not only for this, but like this literally sparsifies my graph and it's cut sparsifier, okay? And we saw the proof of this, that, oh, and this happens with probability 1 minus 1 by poly n, as good probability as you like. So this is like with very high probability, right? By adjusting some constants here, you can make it as high probability as you wish. Okay, so what will be my static algorithm? My static algorithm, so how will I go about my getting a static algorithm, right? So my static algorithm will be, forget about dynamic, nothing. Like if I gave you this lemma, so let's first give a probabilistic construction of a sparsifier, like algorithmic but randomized construction of a sparsifier with not too many edges, okay? Okay, okay. So let's see, G0 is my G, okay, in the beginning. Now, what I do, I take out any edge which participates into any lambda star cut, right? So what, so I fix, okay, let L0 be the set of edges in G such that how should I write? Okay, such that lambda of G minus L0 is strictly greater than lambda star. Okay. So L0 is those set of edges which after I delete, the min cut of the remaining graph has increased. And how I can do this? Well, I first find an edge, I first find a min cut, right? I check, I can find min cut in my graph. So this is an algorithmic construction. I can find min cut in my graph. If it is more than lambda, L0 is 0. If it is less than, I delete this, right? Now look at my remaining graph. It could very well be that there is still a min cut somewhere hidden of size at most lambda star, right? I delete it again. I keep doing this. How many times will I do this? Every time I delete a lambda, I delete a min cut, the number of connected components increases by 1. So I cannot do this more than n times. Right? Every time I delete this edge, some connected components like disconnects. So the number of times I can do this, at most I can get n number of connected components, which means that if I do this process, number of edges which we will ever add to L0 is never more than n log n. Right? In fact, over all the process. So, but I can find L0 like this, right? I'm anyway hoping to get a graph which has an Sparsifier of n poly log by epsilon square. So this is perfectly fine for me, okay? Okay, so what do I do now? So, given a graph G, here is my G0, L0, okay? And from here, what do? I construct G1 by sampling each edge with probability half. This is what I do. This is what this construction does, right? Now I can apply this construction and I can get G. What is the property of G1? It is a very good Sparsifier for this. We'll prove this. Now next, what should I do? Okay? Okay, great. Now what I do, fine. I mean, if I really want to, now this graph G1 has much less edges. In expectation, it has just half the edges of this, right? So now again lambda star cut could come out, right? Because lambda star is with respect to number of edges. Forget about weight or something, because that may not come. But as respect to number of edges, because this is what we needed, the number of edges which are going across is sufficiently large, okay? So suddenly more set of edges could come across, right? So I find another one, L1, okay? Again, what is the property? Lambda of G1 minus lambda 1 is greater than lambda star. I again apply by sampling each edge with probability half, okay? I get G2, okay? I will another construct L1, L2 and do this until unless I get to GT which is empty, okay? First of all, in expectation, T should be like roughly log n, and you can prove that with very high probability, like even if T equal to 2 log n steps, if you do this, your graph will be empty, okay? Okay, so what I'm going to return as my Sparsifier, okay? So let's let's prove that everything is a Sparsifier of previous thing. Everything is a Sparsifier of previous thing, okay? Okay, so what I will show to you that G1 is not L1. G1 is a Sparsifier of G0, G2 is a Sparsifier of G1 and so on and so forth, okay? But what will I show to you? Okay, not G1. What I will show to you, this is a Sparsifier of G0, okay? This is a Sparsifier of G1 and so on and so forth, right? So now let's try to show, okay. So let's first show this, that G1 union L0 is 1 plus epsilon Sparsifier of G. Let's show this, okay? And that's very easy, okay. What do I need to show to you to show that? I need to show, okay, let's look at lambda for some A, lambda A in G1 union L0. Let's look at this, okay. So what I'm going to show to you, in fact, 2 times G1 union L0 is a 1 plus S Sparsifier of this. Means I have multiplied every weight of G1, every edge I have given weight 2, okay, but nothing to L0. L0 is just 1. So what is lambda A of G1 union L0 is going to be equal to, I shouldn't write lambda because lambda denotes cut. So let's write capacity of G1 union G0. What is this equal to? I mean, I can work with lambda itself, it's not a big deal, but that's fine. So what should I show here? I need to show this is less than equal to 1 plus epsilon times lambda A of J. This is what I have to show. Okay. Now, what is capacity A of G1 union L0 is less than equal to now edges which are going in G1. So let's say capacity 2 times, okay, I shouldn't, 2 times lambda A of G1, like edges, look at A, right? A is here, like some edges are going here and some edges are in L0, right? Plus lambda A of L0. So think of L0 as a graph with vertex at V, okay? Think of this. So union of, and these are edge disjoint. So look at A, some edges are going here, some edge. So this is what is edge in G1 union L0 graph. Okay. Now what do we know by the probabilistic construction? This is equal to 2 times this is equal to less than equal to 1 plus epsilon times lambda AG. One plus epsilon times lambda A G plus lambda A L0. Okay, but what is lambda A of G? No, this is not correct. This is G minus L0, right? Because this is what I applied my sampling to. Okay, but what is lambda A of G is same as lambda A of G minus L0 plus lambda A of L0. This is exactly what lambda A of G is, right? I have taken his edge which is in G minus L0 and which are present in, which implies this is 1 plus epsilon times lambda A of G, because take 1 plus epsilon here, then you will get this which is equal to this. You can similarly prove the other inequality, okay? So what did we show? We showed definitely this guy is a Sparsifier of this. Let's try to show this guy is a Sparsifier of this and we will do exactly the same thing, right? But forget now weights, like now we forget what weights we have put, we will just presume that it's fine, like it's unweighted graph, right? When we will go to the G, we will do these things. All I need to show that this is a Sparsifier of this with something, okay? Okay, so what I would have done, capacity A of G2 union L1, right? Capacity of A is G2 union L1, this is what we want to show, right? G2 union L1 is a Sparsifier of what? G1 L0, G1 minus, sorry, just of G1, right? Just of G1. Okay, fine, this I have to show this is what it is, right? Fine. What? Yes. Look, here's my G1, right? I deleted something and did, and I put this together to make a Sparsifier for G1. Okay. So this is what I have to show. Now, what is this? Well, whatever maybe this Sparsifier is, right? Times, 2 times this, 2 times lambda A of G2, lambda A of L1, right? Now I apply the probabilistic construction which I have done here, because what is the because on what is the property of G1 minus L1? Lambda star is large, right? So hence this will happen that 1 plus epsilon times G1 minus L1 times L1. But what is the lambda A of G1? Just number of edges. It's basically G1 minus L1 minus L1. So what you will get is 1 plus epsilon times this. With respect to edges. With respect to edges. But I have used a weight 2 here, right? So what does it mean? So what will be I doing? So now you remember, right? If something is a sparsifier, 1 plus epsilon is sparsifier of something, and something else is a sparsifier of this, then this guy is 1 plus epsilon whole square sparsifier of this. So ultimately what we are going to output? We are going to output, if you notice, so look at GT minus 1, LT minus 1, which gave us empty set. So now what I am going to return as my sparsifier, here I am going to make every weight 2 power t minus 1, right? So my sparsifier which I am going to return is the following. So it's going to be L0 plus 2 times L1, 2 square L2 dot 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 2 to the power t minus 1 LT minus 1, or maybe we should say GT and GT plus 1 is empty. So T is roughly ordered log n, okay. So this is what I am going to return as my sparsifier, right? And what sparsifier this is? This is 1 plus epsilon times T plus 1 sparsifier, which is 1 plus epsilon times order log n, which is log n. So this is my sparsifier, okay. And why why I am weighing every time by 2? Because look, here whatever the weight was, now I have to multiply with 2 to make it. So this is exactly what this is why this I am doing. I am not doing anything else, right? So this is your static sparsifier, and how many edges do we have? Well, L0 can have at most n log n edges, so can be L1. Right? This is why we were talking about edges, not capacity. I mean, you could also have talked about weighted min cut, right? You could also talk about weighted min cut, but then the cut size and this, it is not with respect to weight, right? It is with respect to number of such edges. And this is why we are talking about with respect to edges, not with respect to the capacity. But whatever we are proving is with respect to the capacity. Look, I cannot say that number of min cuts of this weight is this much, which is a crucial part of my proof. Okay, so this is what I will return, and this will be 1 plus epsilon to the power t plus 1 sparsifier, which is 1 plus epsilon times log n, and if you choose epsilon appropriately, this will be some 1 plus epsilon prime sparsifier. Okay, but how many edges did we use? N log n edges at most. In fact, not even n log n. You will never get more than n log n edges, because look, what are you doing? You have got a connected components. Right? You can never get more than n connected components at any iteration, right? So total number of edges you would have removed is like n log n. But even if you do worst case, n log n, n log n, n log n, n log n, some n order log square n. Okay, but lambda star, right? Lambda star is epsilon. This is what I'm trying to apply.
So you are removing that many edges.
No.
L is a cut, right?
No, but that doesn't mean that my remaining graph. What makes you that G0 minus L0 is not one cut? If I delete just one min cut, that doesn't mean that there is no min cut of other small size. So I have to take all of them, right? Okay, and this is why you get epsilon square here, because you are looking, right? So basically you will get big O of n log n epsilon square size, n log n epsilon square cut size, sparsifier. Okay, and if you remember last time I told you that there is a static sparsifier without log n, and that requires a lot of hard work. Okay, but you can actually get rid of log n, which I don't know how to do it. But this is a simple construction which uses n log n. So what did we do? We had this nice lemma, probabilistic lemma, right? Each time we remove all small cuts, put all those edges in my Sparsifier. From the remaining graph, I randomly pick half the edges, okay, with probability half. Find, great. If it is too large, I like till it is not empty, I keep on finding min cuts and keep removing. And if I'm removing some edge in round I give its way, I weigh it with 2 power I, and that's it. Right? So if you notice, if I would have started with some weights on the edges in the beginning, what I would have done? Nothing. I would have like think of this as edge in the last. What I've done is that if that edge survives, I would have taken 2 power I times that weight, and that would have done the job for me. Right? But it's much easier to talk in terms of unit cost. Okay? So this is what we did. Okay? Now the question is, how do we make it when edges are coming, alright, and at the end I should output you a Sparsifier of roughly this size, right? How are we going to do all these steps in streaming, okay, where both edges can be deleted and edges can be added. Okay, so this is what we will do next. So there are several things, right? Okay. So last time we saw what is called K-edge connectivity Sparsifier. K-edge connectivity. K-edge connectivity, right? And how did we made a K-edge connectivity algorithm in this? So what we did, we took K instantiation of constructivity A1G, this is like A2G, AKG, and what was this? This was our connectivity sketch. Okay, this is our connectivity sketch. We took K instantiation of connectivity sketch, right? K instantiation of connectivity sketch, and what algorithm actually we were trying to do is very simple, right? We said that G is K connected, K edge connected, if and only if F1 union F2 dot 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 Fk is K edge connected, where Fi is a spanning forest of G minus union I equal to J equal to 1 to I minus 1 Fi. Is it correct? F1 I want, F1 is a spanning forest of G, right? So J equal to, no, this is something, what should I say here? G, right? Wait. Huh? Correct, no? J equal to 1 to I minus 1. So what is? Yeah. So what is F1? It's a spanning forest of G minus 1 to 0, which is? Okay, fine. If you're happy with this, so fine. I mean, you understood what I wanted to convey. I mean, there's some coordination, so let's not waste our time, right? So this is what we try to implement. And how did we implement it? We said, hey, look, we have K instantiation of connectivity sketches. We will use this guy to give us F1. We will use this guy to give G minus F1. We will use this guy to give G minus F1 union F2 dot dot union Fk minus 1. This is what we said, right? F1, G minus F1, this, right? And what was the point? The point was, look, and why were we using this independent? Because then it really becomes independent with respect to this, because he doesn't know that we have F1 in head, right? The A2, because these are completely different random sources when we were instantiating each of this L0 sampling, right? So when we were making A2G, he doesn't know what F1 we have here, right? So with respect to F1, this is completely random. With respect to F1 union F2, this guy is completely random, and this is something which you have to. So I could not have just used this and say, get me F1, get me F2, get me F3. No, I cannot do that, because once I fix F1 from this source, now it depends on each other. So they are no more independent, right? And our matrix told us that, look, if you fix a vector and then choose a matrix uniformly at random, then that will work very good with very high probability. But once I have fixed F1 and my matrix is also fixed, there is no chance that it will be good for F2 too. Okay, so this is what we said. But we also said something much more interesting and important. Okay, and that is something let's try to understand. Okay, we also said that an edge E is in k minus 1 cut, at most k minus 1 cut. Edge E is in at most k minus 1 cut of G if and only if it is present in this, right? If and only if this is, right? But how are we doing this? How are we doing this? How are we finding L0? Let's try to concentrate on L0, right? So first of all, to do this, what should I do? I should apply k equal to lambda star plus 1. Clearly, it is going to store all edges which participates into cut of size at most lambda star. Okay. But does it mean that, how are we finding L0? We found first 1 k minus 1 cut and deleted it. And then we found another one. How will we do this operation? Do you understand what is happening? Look at the set of, first of all, there are several issues with this. Let's all the edges which participates into, say, min cut, for example, okay? I delete these edges. There could be new set of edges coming in which becomes part of min cut now, of the remaining graph. Do you see this? So they were not min cut before, but they became min cut now, right? So some edge which was not participating into lambda, look at graph G, look at all edges which participates into min cut, all edges which participates into min cut, right? Let's take that out. Does it implies every edge which participates into the min cut? Does it imply that after I delete this, there is no more min cut? Like suppose, or rather min cut is a wrong word, okay? So what I am saying to you, fix a cut lambda, okay? Look at all edges that participates into cut of size at most lambda in G. Let's delete them. Does that imply that in the remaining graph there is no edge which participates into cut of size at most lambda? Clearly it was not participating before, because otherwise we would have gathered them. But could they participate now? For example, look at cycle, right? Look at cycle, and maybe no edge was participating into cut of size 1, because no edge, but maybe after I delete some edge, now every edge participates into cut of size at most 1. right? So edges which were not participating into small cut could start participating into a small cut after a delete an edge. This is like a stupid example, but
Are we saying that the size of small cut will increase and then so let's start with G.
yes,
We took out some edges.
of particular, look, I fixed the word lambda star. Any edge which participate into lambda star cuts of size lambda star, I deleted it. Look, my process in the beginning was very simple. What did I tell to you? Oh, if there exists a cut of size at most lambda star, delete it. Keep deleting it until there is no cut of lambda star. This is perfectly perfectly correct in a static setting. But I would like to implement this in a non-static setting. Okay, and to do that, I first ask which all edges are participating into the cut of size at most lambda star. Because what did this lemma tells me? This lemma only tells me that if I am able to capture you all those edges which are participating into cut of size lambda star plus 1, at most lambda star plus 1. This is all that this tells me, right? An edge is in this cut if and one. So I can get those edges. But does it imply that if I delete all these edges, is it all that L0 contains? This is my question. Clearly L0 contains all these edges because they participate into small cuts, right? But is that all that it is? Look, I never bothered about L0, like what it consists of before, because all I said, I greedily keep doing it, you will never delete too many edges, so it is perfectly valid for me. But now it could. Okay. So what is our algorithm doing? Our algorithm was doing following, if you notice. Okay. So let's fix the sets S1. S1 is cut of size at most, some fixed cut of size lambda star, at most lambda star, S1. What we did? We said, okay, let's consider G minus S1. Okay. Okay. So G minus S1. So the way our operation is working. First, we have G. I find one cut of small size. This is what greedy algorithm was doing. S1. From the remaining, I was deleting something else, S2. From there, I was deleting S3 till nothing was possible, right? Till I kept on deleting till lambda of this is strictly greater than lambda star. This is what I was doing. Delete S1. From the remaining, delete S2. From the remaining, delete S3. This is what I was trying to tell before, right? So now I want to capture whole of this L0. Right? How do I do this? Okay. All I have is that, look at this F1 to Fk. Now for when I apply with lambda star plus 1, it contains all the edges that participates into cut of size at most lambda star, and that I can check by looking at here. That's enough. So I would have captured some edges here, but have I captured L0? Right? Do you understand my point? Right? You fix a number lambda star. Now you have a static graph, okay, G, and here all edges that participate into lambda star cut. Let's call it E1. Is it true that lambda of G minus E1 is more than lambda star? Huh? Do you think it's true? No. If I delete some edges, remaining graph could have lower connectivity.
Some edges, all the edges which are
Currently participating into lambda star cut, but maybe there is some edge which does not participate, but after you deleted some edge, it participates
in min cut.
in some cut of size lambda star.
Every lambda star cut in the
Any?
Lambda star cut in the supergraph will also be lambda star cut in subgraph.
I didn't get your point.
Like if f1 to fk
Hmm.
is a subgraph of G,
Yes.
and every lambda star cut in the supergraph is also a lambda star cut in the subgraph.
Yes.
So if you're enumerating all lambda star cut in subgraph,
Yes.
you will also enumerate all lambda star.
This is not what I'm saying to you.
Other direction might, but we don't need other direction, right?
We need other direction, right? What are we doing? From the graph, I'm deleting all cuts. Look, what I was doing, I was deleting a lambda star cut. Then I'm deleting another lambda star cut, right? But I'm deleting this lambda star cut where? Not in G. What does this tells you? A edge which participate into lambda star cut in G is preserved here. But what has told you that a edge which is in the lambda star cut of G minus S1 is also present here? Who has told you this? Look, all it tells me that if an edge participate into lambda star cut in G, that is definitely preserved here. It's if and only if. But what I told you that after in G minus S1 I find a lambda star cut, that is also preserved here. Who has told us this? Right? And after I delete an edge, then edge which was not participating into lambda star cut is now participating into lambda star cut in the reduced graph.
Can't we use the connectivity sketches again after deleting one cut?
How many times will I use this?
Log in this connectivity sketch.
So are you trying to tell me that the number of min cuts is only log n?
L0 we can delete, but after that we do not know how to get G1 minus L1.
Oh, we will know. Wait a minute.
So then
No. What? Forget about that. How do you? I'm not even clear. How will we get L0? We are only talking about L0. We are not talking about L1.
Even then, like S1 is there in
first one will get
What?
G minus S1. S1 we can get from this connectivity.
Now, from where do I get S2?
like from f1 to fk you can do S1.
Okay.
That will be a subgraph
G
of G
minus
minus S1.
S1 you just run
So?
the connectivity sketches again.
Connectivity sketches on what? I mean, some of these things are correct, but you need to say in a right way.
Yeah, so that is subgraph of G minus S1.
Which one?
S F1 union of Fi.
But what makes you that this is also a spanning forest of that?
Yeah, but S2 is now a subgraph of S2 is a cut in G minus S1, and hence because this is a subgraph, S2 will also be a cut of.
But maybe S2 edges are not even there here. Look, I need to give you an answer, Sparsifier, I need every edge of L0 being present. Where do I get it? Look, what I was returning you, L0, L1, L0, 2, L1, 2, L, 4, L2 and blah, 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 blah. How do I know that now it's there? Yeah, it's a subgraph, great. So you will find something. So does that imply that is equal to L0? So like, look at your S2. Huh?
Which is also fine.
No, we will not get. What makes you sure that some edges, I'm not storing all the edges here, right? Then,
So here
look, I need S2, right? I need all the edges of S2. Not all the edges of S2 are here. It became a different spanning forest where it became.
S2 is also a lambda cut, right, of G, and because of the property of
No, S2 is a lambda cut of G minus S1.
After we get G minus S1, the remaining one, if we just in G minus S1, if we decompose it into F1 union Fk minus 1 again by using connectivity sketch on G minus S1. Now from the new F1 to Fk minus 1, you find out S2.
Why if I do, why after I delete S1 you're guaranteed to give you, this will give you a spanning forest? Suppose after deleting S1 graph has a spanning tree, why are you guaranteed that this will give you a spanning tree? I am deleting some edge, right? So what, that is very easy, right? I have this sketch edge, I want to delete some edges, I go and delete this edges, and now I want to get some F1 tilde. Why? It all guaranteed that it, if you go back, all it said that I will support an edge. And with respect to that help of support of an edge, I was able to get a spanning tree. Now you deleted some set of edges, and now you want my data structure to again return you a spanning tree. I didn't guarantee you that until unless you use something else. But that is not the only thing which is, come on, that's linearity is fine, but there is some probability computation happening, right? Random with respect to this, random with respect to that. Okay? What? If you have a question, please ask me. I mean, look, these are not data structure of your usual sense. They're probably they are happening with certain probability, right? They support something with one, just all they can do, each of these guys can do is give you just one edge incident to it. That's all, right? So, but my matrix was random, right? Can I utilize that fact, right? Can I make this Fi from, like, you will see what I'm trying to tell you, okay, in a minute. It's
Can't we choose this A1 to AK uniformly at random from some other family?
what family?
Every time, I mean, so.
But then that will be like, then I will be using n square space. Okay, let's define, I'll tell you what I'm going to define recursively some object EI. Okay, so what is EI? Okay, so let me define lambda E of G. What is the meaning of this? Okay, E participates into min cut, okay, into a min cut of okay. So what I'm going to define lambda E of G to be the minimum cut that E participates into, okay? Okay, of a cut. Okay, this is what I want to say. Okay, this is what lambda E will mean. Okay, so now I'm going to define a notion. What is EI? E in E, okay, and lambda E of G minus j equal to 1 to I minus 1. So recursively I am going to define j minus 1 ei is less than equal to k. Okay, so with respect to some number k. So this is what ei is. Okay, and I am going to define light edges that, or light kg, light of kg is union over I going from 1 to 1, I equal to 1 ei. Okay, what does this mean? Look, this tells us all those edges which participates into cutoff size at most k. Let's delete those E1. What is E2 will be all those edges which participates into cutoff size at most k after I deleted all the edges in the beginning which participated into the cut of size. And I keep on doing this till when will it stop? When no more, like this becomes empty, right? I mean every, so what is that at that point of time if I delete this edge, so this is what I call light of j. So notice this is exactly equal to L0. Is this fine? Look, what is the first thing? I looked at all the edges which participate into cut of size lambda star, cut of size k. Fine. So they already participate in this graph. I deleted this because those edges must be deleted because they are part of small cut. Every one of these edges. Fine, I deleted it. Now if there are some more new cuts arises, those goes into E2. If then I deleted them further. So what did I do? This is exactly echoing this process, right? So this is exactly equal to L0 which I am looking for. Okay. So why did this process stop? Because every edge, the minimum cut which participate has size strictly greater than k. Okay. Now notice what happens, and this is something which is a very cool thing. Okay. So I am going to call this BG, and this is also called a skeleton or a sketch, whatever you call, like whole together. Okay. Okay. So BG is a skeleton that returns, and this is very important, that returns an arbitrary, let's say k plus 1 is a skeleton, BZ is a skeleton, okay. BG sketch. So what I am going to call skeleton. Okay, we will call this K skeleton. Okay. Okay. BJ is a sketch that returns an arbitrary K plus 1 skeleton. Okay. Of G with probability what? With failure probability sum 1 over NC. It fails with probability 1 over NC. Okay. Since, look at this, E1, E2, dot, En are sets that are defined by what? That are defined by what? This is a property of graph. It is not a property of any randomness. These guys are fixed from up prior to what sketches I chose. So my sketch is a random with respect to all these guys. Do you understand? This is a property of graph. Right? This is not a property of my sketch. It's not that, look, why were people not able to, because this randomness produced F1 and now I cannot use this randomness to get another F2. But look at this E1, E2, En. These things I know a priori. Like looking at the graph, I know this thing. This is a property of graph. They are not property of my sketches. And this is something which we need to use. And this is why you can delete these edges and you can do this and you can do this. That is because these objects are not dependent on your randomness, but these objects are fixed already from the beginning of the graph. That are defined solely by what? G. And not any randomness. And this is very important. Okay. Otherwise, I cannot use. So look at the edges which are in E1. Hey, this guy doesn't know these things. This skeleton doesn't know that this is what E1. It's just that because we had lambda star plus 1, this guy contains E1. But this E1 is fixed. Like irrespective of what randomness we have used, E1 will be here. Right? Because this is a property of a graph. This is not property of randomness. Okay. Look, even if you did not tell you a sketch and all, like I can get U1, I can get E2, I can get E1 by looking at my graph, not looking at my randomness, right? Okay. So what does this imply? Okay. So since E1 are sets that are defined solely by G, okay, we can specify the fixed event. It's a fixed event. Okay. What is our fixed event? Let's write down. Okay. We fail, okay, will fail to return k plus 1 sketch, okay, k plus 1 skeleton sketch of k plus 1 skeleton sketch of G minus EI, okay, given B G minus I think it should be EI minus 1. Yeah. G minus given this, okay. So this is fixed. Bi will fail to return this sketch given this, right? Now how many such events are there? N events are there. So I can apply union bound, right? Because these guys are fixed. So they are not dependent. Like E1 is fixed, E2 is fixed, E3 is fixed, E4 is fixed, En is fixed. So what I'm asking, oh, what is my probability that this is not going to give me a skeleton or a sketch of this guys, right? Its probability is again some 1 over n power c. Right? So if I take union over all these events, I will get something like 1 over n to the power c minus 1, and that's great. Do you get me, Ranka? So what you don't get? Do you understand that these EIs are fixed? Right? So if EIs are fixed and I have a random matrix, what is its behavior with respect to fixed people? It's going to be random, right? So each of these, then hence I can take union bound, because for them each of these events are independent events. They are not dependent on each other. Happening of E2 is not dependent on E1. For example, here I could not have used, look at A1G, I got F1. Ideally I would like to get F2 equal to A1G minus F1. Right, which is correct, A1G minus A1F, right? But I cannot use this to get my F2 out, because why? Because F1 is produced by A1. So I have used this randomness. So A1 matrix is no more random for G minus F1. But here for E1 it is still random. E2 it is still random. Like imagine yourself, nobody told you this graph. I didn't show you this graph, right? I did not even show you this graph G, right? Because what is my sketch is doing? Some edge comes, does it look at whole graph? Nothing. Edge comes, it inserts something, some edge comes, it deletes something. It doesn't even look at the whole graph. But if some properties of my graph comes, which is already predefined, which only depends on this, not on my sketches, then I can use the same sketch to produce again and again and again and again the same set of things, right? Otherwise I cannot. So now this is very clear. What will I do? Well, where is my E1? E1, I look at my first skeleton, you gave me this, I just do only one, this BG, I get F1 to FK, I said, hey, give me all the edges which participate into cuts of size at most this much. In this graph, it gave me, that is my E1, because this is precisely those edges which participates into G in the cut of size lambda star. So this is what I got, my E1. Now I need to do this with respect to, I need to find it with respect to E2. So now what will I do? I will find, now look at BZ, G minus E1, right, which is same as BG minus B times E1. And the point is, since these EIs are fixed, B is still a random for this, right? I did not produce these EIs just like, of course, this is the property of, if this is a k minus 1, if this is a k cut preserver, then it is a property of the graph that every cut edge which comes here preserve. So now what will I do from looking at this? Okay, I know all the cuts of G minus E1 which participates into this cut is here. So I find this E2. Okay, I keep doing this until I cannot find this. Then what did I find? I found my L0. BG is this whole skeleton, union of all this. So what will, if I will find E1, what will I do? I will go and delete E1 from here, E1 from here, E1 from here. Okay, then I will get some another F1 tilde, F2 tilde, Fk tilde. This is my second thing. I will find another cuts there, that's my E2. In the remain, whatever is left now, I will dilute E2, 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 E2 from here. From there I will get some F3 tilde, like some other F's from here, take their union, find another E3, keep doing this. And I can do this poly times because these EIs are fixed evens. In the sense, these sets are already predefined, they are property of my graph. So with respect to each, look, the guy doesn't see this, right? What does our matrix told that? A is random with respect to every x in Rn, right? So in particular it is random with respect to E1, in particular it is random with respect to E2, in particular it is random with respect to E1, En, because these guys are not dependent on, I did not construct these EIs looking at E, looking at G I constructed these EIs, right? So if I have some properties of graph, then the same matrix will be happy. I can work with them, okay? So what does this imply? That I can find my L0 very nicely by just one sketch, okay? Okay, so at least this took me a lot of time to understand that why they are using this sketch, because they do not write much here, but this is the reason why they can do this, right? Because our EIs are not something which depends on the randomness, but it's just the property of the graph which we have seen. Okay, so we now know how to get handle of L0, but we have to also sample each of these guys, no? So how will we do this sampling? Right? So like I do this, this will give me E2, B of G minus E1 minus E2 is nothing but B of G minus B of E1 minus B of E2, again use linearity, I'll get E3 from here and so on and so forth. So I know, so I told you how to get L0. If you give me a sketch of G. But now I need to give you a sketch of this. I mean, next time if I want L1, I want G1. If I want L2, I need G2. So how should I go about it? How will I do this? In one pass. Okay, so we'll make several data structures for each of these guys. Okay, so let's now have to write in terms of, let's call it B1 of G, edge comes, it could be either plus or it could be deleted, minus. What will I do? I will definitely put in E1 because that is like G. But to go to G1, what I should do? Right? I have to toss a coin and then put it inside. Right? What? No. I don't care. G is completely here because that is with probability 1 over 2 power 0. So that's perfectly fine. Now for each edge which is here, I will do the following experiment. I toss a coin. Okay? So for an edge to go inside, our sequence will be head. For an edge to go into the second, sequence will be head, head, blah, blah. So first, now edge comes, with probability 1 I have put it, now I toss a coin. If it head comes, what should I do? I place it here. But now that edge could also be here, so I toss another coin. If it comes 2 heads, I also go and place him here. Oh, if it can be here, it could also go down, so I toss the third coin. Oh, if it also comes head, I also place it here, and so on and so forth. So because look, an edge which is present here only goes down, right? Which we lost. So this is how we put all the edges. And if edge is deleted, I just go and delete from everybody. If it is not present here, it is not present here. Perfectly fine. Okay. Is the data structures clear? Right? This is what.
When you delete an edge, you're doing minus of that edge's existence.
Yes.
You might not know if that edge exists because you don't know, you can't look at G2.
No, I can't look at G2.
So how do you know that edge exists?
If this edge did not exist here and I deleted it, what effect it will have?
But you're doing minus of some adjacency, that might have some, you're changing the matrix, right? Ideally,
So?
your thing should be same.
So what? Look, I looked at this edge. If this edge is not present in the graph which it represents, if I delete, should it have any effect at all? Look, this is a graph which represents the current graph. I deleted this edge. Then it will have its effect. If some edge is not present in my graph, should it have any effect?
Like you have a matrix that represents that graph. Right?
But no, this is a matrix which represents the graph which is here.
Yes.
That's it.
So, and now I'm doing minus some edge.
Yeah.
So my new matrix will be matrix of this minus the matrix of edge, like by linear. And then because the minus matrix of edge is changing the matrix. Ideally, I want the same matrix.
If this edge is not present, should I be deleting it? Because what I'm doing, I'm subtracting something and adding something.
Each one of the log n levels has a separate sketch present for them, right? So when you have to delete an edge, you can just go to that sketch and just find out if that edge is there in the particular thing. At most, we can take log n steps to know in which level an edge is present, and then delete it.
But so on the edge, right? So we don't know if the edge is present there. We don't know if the edge is present there.
But you can spend some log n levels for for this L0 to L log n and try to detect if the edge is present or not. I mean from the sketch. Each one of the log n levels has a sketch with it. So we can detect the edge from there. How?
Okay, so let's see if I have a matrix A. So what matrix I had, if you recall correctly. So the matrix which I have, where I am making this is, we had this big matrix A with right. We were multiplying this with this edge vector, which was something something. Okay. Suppose this edge is not present in this graph. Let's see what effect does it have. Do we get a new edge? See what I'm saying? So what we were doing nothing, right? What we were doing that if edge comes, and these columns were for edges, if I recall correctly, right? A particular what were we doing? If you recall correctly, particular ij. So suppose this edge is not, if this is present, then we are doing nothing bad. But suppose this edge is not present, right? And we did this operation. What changes does it do? Does it add an edge to the graph? Does it not add edge to the graph? If it does not add edge to the graph, then we are very happy, right? And in my head, it shouldn't add edge to the graph, right? So what is the meaning? So look at, so some edge has, I would like to delete it. But here, this is, look at the vertex I and look at the vertex j, right? Suppose I is less than j. Suppose I is less than j. So what is the property here? It is 0 here, it is 0 here, right? Actually, the whole column is, yeah. Look at a column, no, what I am talking about.
How exactly is it happening? Like, it can also happen that with probability half you have an edge in P1. With probability 1/4 you have an edge in the next level and so on. But it's like maybe the edge is present in all the levels with some lower probability when it goes down.
Yes, it happens.
So it's present in all the levels.
Yeah.
An edge.
Yeah. An edge is present in every level with some probability, right? But that lowers down, right? Because I was doing this random pointers. So it is chances that I can get head, so I go down, right? but in expectation I will not be going too much, that's it. So like in certain number of rounds, because anyway it's probably, so every edge is present in this. But suppose this edge is not present, and so whatever we do, so look at what was this matrix doing. This was like, so this was a big matrix, it was of dimension what, log square n times n, n choose 2, right, n choose 2 here, and this is basically representing an edge ij, right. So now this was anyway a random matrix where we had put 1, we constructed this matrix randomly if I recall correctly, and here it was with probability something like 1 or 0 with probability something 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 in this particular column, am I right? And if the way we were constructing, if this edge would have been 0, like, so in this particular vector, this whatever may be this, it is going, its contribution is going to be 0 to the sum. Look at this vector and this matrix, right? Because currently this edge is not present, what happens? This is going to be 0, right? This is going to be, if I multiply this with this vector, I am going to get a 0 matrix, because this whole vector is 0 vector.
That is some vector, right? It's not 0.
No, it is a 0 vector, right? Look, what were we doing? We had a matrix A, right, which we had this matrix A with, where we had this geometric sampling, and now we said that okay, if you give me this any vector which is non-zero, then I will have a vector log squadron which will be, by looking at which I can extract out non-zero entry. That's all that I said. Okay, and then we were saying that look, so which means that okay, now when new edge comes, right, what is this? New edge is being deleted. What we were doing is we were maintaining this for every vertex we were maintaining, right? For every vertex we were maintaining several of this, so that I can get an edge adjacent to it, right? So what we did last time was that okay, suppose now there is an edge ij which is being deleted. I want to go and do some operation to this guy. What was the operation we were trying to do? We were trying to do this operation is that to v we were going to, if suppose I is less, we were adding -1 somewhere and looking and doing some contribution to this, and similarly here to the j guy. But suppose there is no contribution, does this add contribution to that? Does it add contribution to this? Because we cannot remember these coin tosses, right, which we did when an edge comes, because that's too much. Okay, I will look into this and tell you. I'm not able to think through at this point in time. Okay, so for now let's just believe that they are just edges are being just added. Then we can definitely do these things. Okay, and okay.
Instead of vector containing just ones and zeros, if the edges are added or not added, can we replace it with the probabilities with which the edge is present in that level? Then try.
No, because all we want from each of these guys is some connectivity. So no, we cannot do that. I'll tell you there should be some easy fix for these things. I just don't know this literature that well enough. Okay, so this is what we do for now. Let's just assume that edges are just being added. Okay, and then we just do all this, and Now what happens? Now that we have to give, so basically we have, this is basically our B0, B1, BT. So now this will give, notice what happens. Maybe some edges of L0 are present here. It could be, right? Definitely here all the edges of G is present. So from there we will get L0. But I didn't know whether this edge present in L0 or not. So with probability half I pushed him down. Right? But that's very easy because once I get this L0, next time I will just ignore those edges. Right? So I will not look at, like, what will I do? Right? So basically I think there are samplers which does this kind of job. I mean, okay. Okay. So actually there are sketches for doing this uniform, like one is content, they are called something S0, S1, right? And then you apply your B on them, but I thought that maybe we can do something clever. But if you notice that this will give me L0, right? Now I need to delete L0, but that's perfectly fine for me, right? Because again this L0 and L1 are properties of graph. They are not properties of, right? The way these E1, E2, En are sets that are defined, they are properties of my graph. That's okay. So now what will I do? This is completely different set of random bits compared to L0. So I cannot use the same for L0. So now next time when I'm trying to find L1, I will ignore all the edges in L0. Right? From here, I want to find now L1. How will I do this? I will ignore like if I find something, so I got L0 completely in my hand with good probability. So if I encounter an edge of L0, I will just ignore that, right? So first I will delete L0, right? And then, but I don't know whether L0 is present here or not, as you said just now. So I'll get my sketch, okay? If this is present, right? Then I will just delete L0 and only work on. So I will delete, so if I find some spanning tree, I find some edges of L0, I delete L0 edges, I again find a spanning tree here because time is not a constant. Again I find some, so I keep doing this till I forget about L0, I got something, I will extract it and I keep doing this till everybody else, right? So you get L1 here, then L, and that you can do because L0 is not dependent on this matrix. L0 is dependent on this set of randomness. Because look, why now it is important? Because L0 is fixed, but what is L1 depends on the random graph you have constructed with probability half. So now this L1 depends on this. But once this graph is fixed, this L1 is fixed, right? But construction of this sketch depends on the construction of this sketch. So what graph you get here is not, it depends on this sketch. So I cannot use this sketch to carry out my all operations. So this is why L0 I have here. I use this to get my L1, but I can ignore L0 because that is completely independent of this object. Similarly, I can go and do these things. Okay. So this is how you find Sparsifiers in streaming, and I didn't tell you how to do it in what is that called? When edges are deleted. I'll try to tell you tomorrow. So notice that what is this Sparsifier? This is like Sparsifier with 1 plus epsilon times 2 log n, right? Depth. So if you set epsilon equal to gamma times 2 log n and run this whole process, you will get something like 1 plus gamma Sparsifier, right? 1 plus gamma Sparsifier of size what? 1 over n power polylog n, because you have to keep lots of things. And you also will have some epsilon square somewhere because they are inbuilt in these things. Okay. So this is, if you have patience, you can read it. Guha, McGregor, Tench. not C, 16. It is with S, not with C. Okay.